生的时候，医学系的学生，我还可以用英文到了物理系的学生，我有时候用英文，也有一点点国语有一期我的物理系的学生上完课以后，有个女同学走前来，送了一个粉红色的卡片给我。他说：“亲爱的翁老师，你的英文很好听，国语很可爱，但是我都听不懂。”这个卡片我再给大家。Okay, I will use English in most of my talk. Okay. So it is really my honor, and I feel very blessed to come to share with you my mission for the past 40 years and the coming years. My mission. So the title of my talk is Mission. The mission possible. And NPM B23 is the nucleus protein I work for more than 40 years. And this gene, in recent years, we finally established the gene co-expression platform. We find out this cover the origins of cancer, no disease. Okay, let's start the mission. In fact, cancer was first described in the years of 1845. Children and adult leukemia prognosis was clean at that time. This disease was described in 1845. Death, often painful, usually within weeks of diagnosis. Also, 100 years, symbol of medicine's long-standing powerlessness against disease. Essentially, there's nothing for therapy. Death, nothing for therapy. After 100 years, in 1947, a Harvard graduate, C.D. Farmer, a resident pathologist at Boston Children's Hospital, he asked simple questions. In India, vitamin B12 and folic acid can intervene or cure anemia. Could we block the folic acid to cure leukemia? A simple question he asked. After 100 years, nothing for therapy. Knowledge ought to have serious purpose. You have serious purpose. You ask simple questions. With passion, intelligence, energy. In 1948, he published a paper in the England Journal of Medicine. Essentially nothing for therapy, but his observation, his question, published a mixture of his belief and his system. A lot of people don't believe. Simple, blocking folic acid can cure cancer, leukemia, big question mark. This discovery, this small discovery, marked the first, but hardly the last. Hardly the last. Dr. Farber overturned conventional medical wisdom. All students in medical field have wisdom. Medical wisdom was we had an advanced against cancer. 1947. 80 years later now. So you can see Harvard Medical School. When you visit Boston, you can visit this very famous Faber Cancer Institute. This is Dr. Faber. Okay. So in the years of 1950, back to the age, in the 1950, about that time, there's a simple question being asked. What is genetic material? Sorry. What is genetic material? At that time, cell biology, in the cell, there's DNA, RNA, and protein. Which one is genetic material? Most people guess protein. Not much people guess DNA, because DNA, too much DNA in the cell, there's so very much DNA, RNA, protein. What is genetic material? There are two observations at Taipei in the year 1950. Scientists observed most of the DNA are localized in the nuclei. This is the first observation. Why they have to be localized in one compartment, nuclei? Or why DNA have to be protected in the nucleus? You see, important thing is protected in the nucleus. The second observation is all the steps. The DNA content, AT, GC, the ratio is always 1. So whenever you see A, you see T. Whenever you see G, you see G. AT, GC. For example, whenever you see me, you see a lady, a beautiful lady. We have relationship. So whenever you see A, you see T. Relationship. What is genetic material? Relationship between one generation to one generation. So at that time, after convert, MD medical student graduate and do research in Corey's lab. Dr. Corey is a couple, doctors Corey. All of them got the Nobel Prize. Corey's story, let me mention to the students. Corey discovered a lot of enzymes. They both graduated with PhD degree, a couple in the class. They graduate, they married, they graduate, they did the research. But at that time, Washington University only hired and employed Dr. Corey husband as an assistant professor. Mrs. Corey, Dr. Corey, only was employed as a research associate, PhD research associate. At that time, Lehman discrimination. When Dr. Corey got a faculty position, the day they announced of the Nobel Prize, the wife, the university announced this lady got professorship. So she was promoted from research associate to professor on the day they got the Nobel Prize. This is not what I was told. So Arthur Conver was working in their lab. He observed these two observations. He said, DNA could be genetic material. If I could discover the enzyme for genetic material, I prove that DNA is a genetic material. Got it? Simple thinking. So, he, using 3 years, 1953 to 1956, he discovered and purified the enzyme for genetic material, DNA polymerase. So this is Arthur Conver. Okay, this is the picture. He talked at that time. I was sitting just in front of his office, a bench. So he was taking these pictures for his talk, The Love of Enzyme. So The Love of Enzyme was written for his 70th birthday. And also at that time I was almost to leave Stanford. So he gave me his book and also with his signatures. To benefit my warmest wishes for your success in science. This is our comfort. Okay. So he discovered and purified an enzyme for DNA replication to prove that DNA is genetic material. Okay. So he opened the field of nucleus, and the first postdoc fellow, Professor Prof, was his first postdoctoral fellow. He uses enzymes in his refrigerator to discover a lot of enzymes and start the genetic engineering. So a lot of genetic genome research is built on the enzymology in build of biochemistry. And also Albert Conver established the first department of biochemistry in the world at Stanford in 1958. So this is a story about how biochemistry start the medicine. Okay, let me start to talk about cancer. Cancer. Why cancer is so terrible? Everybody, when we talk about cancer, we are scared. We're scared. There are 4 major cancer features or properties that cancer scares over these years, even nowadays. Cancer is very invasive. Metastasis, heterogeneity, resistance, invasion, metastasis. A lot of gene play role in cancers. They become resistant, very less responsive to normal control phase. So this is the 4 major invasive properties of cancer. My PhD advisor, Dr. Harry Bush, he did a lot of cancer work, and he's very famous nowadays. After he passed away, a lot of science say that, wow, he lost cancer. Most of the scientists, he lost cancer very well. He wrote a lot about in cancers. Let me tell you his story. When he was an MD PhD student, also asked simple questions. Disease has origins. If you know the origin of disease, you can cure the disease. Then he asked, what is the origin of cancer? So after the classes, he went to the hospital using the microscope to see the cell. At that time, cell biology microscope is really in the high peak. So he looked at the cancer cell, compared the cancer cell with the normal cell. Thousands of cells simultaneously. After several months, he found that in the cancer cell, the nucleus, in the nucleus, is enlarged. Pleomorphic means there are many different ugly shapes. Pleomorphic, ugly shapes. Ugly means cancer. Cancer means ugly. Looks very ugly. And also very hyperactive in the nucleus. So he said that maybe the origins of cancer is nucleus. This is his first observations. So he used his whole life to study nucleolus. So this is how the origin of cancer is nucleolus be determined. Okay. So he using a lot of efforts to isolate the nuclei and the nucleolus of the nuclei, and he studied the proteins in the nucleolus. At that time, 1960, at that period, using 2D gel electrophoresis to separate those nucleus proteins. So there's area A, area B, area C, it's just name 1, 2, 3, 4, just name it. And the area B, there's a protein called B23. There's a C area, there's a protein C23. So it's just a name. So at that time, they got study of B23, they focus on studying of B23 and C23. There are two reasons. B23 is highly expressed in cancer, liver cancer. And also it's phosphorate protein, so maybe involve regulations. So they're interested in B23 and C23. And at that time I joined in his lab. And then I still remember Professor Harry Bush sitting in office with two students, one from MIT, they got a master's degree from biochemistry, I got a master's degree from organic chemistry, so he's more experienced in biochemistry than me. Christopher and Benjamin standing before Harry Bush. And then there's whole protein for us to choose for our study. My name is Benjamin, so I chose B23. Christopher chose B23. This is my mission to start. It's really just like it. And PhD thesis, go ahead. Try to do whatever you want to do. No other question need to be. So I read a lot of literature and study and then start my B23 studies. So this is the way I start my mission 40-something years ago. Okay. Okay. What I did after I took out this project for my PhD program, I published 2 papers on my PhD study. The first paper I found out B23 is nucleolus protein, but it can shuttle out to the nucleoplasm. This is my PhD thesis. They can go out. And then when they go out, it's correlated, associated with ribosomal biosynthesis processing. My second paper. So I got these 2 publications in Cancer Research. This is one very good journal, and I got my PhD. I thought, wow, it's so simple. This is very important one at the time. Nowadays, still very satisfying. And Professor Harry Bush won't be a very good recommendation letter, so I got into Stanford for my postdoc there. Okay. So, B23, a shuttle protein between nucleus and cytoplasm. Not only just in the nucleolus, they can go out. This is my thesis work. And after I graduated, I went to Stanford for my stuff doing basic research for DNA replications. And I got job offers from Chung Medical School at that time. So I went to Chung. My first experiment we carry out is asking, if B23 going out, can it go back? If it go out, cannot go back, can it be reversible? Or when it go out, or when it could not coming back? Just these 2 simple questions. My research associate, very hardworking. My first paper, found out this B23 can go out and go back. Once we do high doses actinomycin D, it could not go back. Why we can publish it in a very good journal in Cancer Research? there's a professor at Johns Hopkins. He found out the same dosage that we use to going out and coming back, or high dosage going out to not go back, the total isomers in DNA being blocked at similar dosage. So these two papers published in one stage issue of the cancer research. We found out this. This is a really important biological activity related to going out and going out. Okay, so this is B23 being shuttled out in doing a lot of biological functions at that time. So almost 15 years ago. Okay, so we did a lot of B23 work continually. So you can see B23 is overexpressed, transformed tumorigenic, oncogenic. B23. So at that time, we also set up a very important platform, cellular differentiation and also apoptosis. We have apoptosis program subject. And we also ask a simple questions. If B23 is so important in cancer, in cancers, can we downregulate B23 in cancer cell, push back the cancer to the normal, being responsive to differentiation and program cell? If B23 is important in cancer, can we push back? So we downregulate B23, see what happened to this cancer cell. So my two PhD, one master student at that time, there's a lady, there's a gentleman. So they carry out this study, one for apoptosis, one for differentiations. So after we downregulate cancer cell, it seems nothing happened. The cell growth curve is similar, a little bit stationary. After a weekend, I told them, say, well, he cannot distinguish from a bad boy, good boy. Give them some stimulation to see how they respond. So they went back to the lab to do the experiment. After we downregulate B23 in cancer cell, the cancer cell becomes 3 and 5 times more responsive to differentiation and apoptosis. We then asked him to do the differentiation and program cell apoptosis, the DNA qubits, all these experiments, differentiation marker, all they did experiment, and we published for oncogene paper in one issue. And the student now has one is now professor in Kaohsiung, one is a professor in mainland China. He's a big professor. His lab is about 20 people, and he's a very, very good professor now. So my two students did this experiment, now become professors. And these two publications is a really hallmark for my mission. Okay? So B23 is very important in cancer regulation for cells responsive to normal differentiation and apoptosis. Okay, studies. Oh, let me introduce you one of very important lady. Remember 1947? From nothing for value, there could be drug value. Because blocking the folic acid can cure the leukemia. This lady, after she graduated, she wanted to go to a PhD program, but she had some illness. So she went to a pharmaceutical company to work first. Hopefully, after a few years, she can go to graduate school. She loved to do experiments. She wanted to cure cancer. Her grandpa died of cancer. She wanted to cure cancer. So she worked on the pharmaceutical company. She never get into the graduate school. Stayed into that pharmaceutical company. She worked very hard. She was the first one She was the first one to introduce anti-metabolite for drug therapy for cancer, leukemia. Folic acid, anti-folic acid, she was the first one. And she got the Nobel Prize for the development of this anti-metabolite nowadays in chemotherapy and also antivirus infections. She never got a PhD degree. She's a woman scientist, got the Nobel Prize, and also, I think the first one, or nobody without PhD degree could get the Nobel Prize. She's the first one. So, she really revolutionized drug development, producing drugs based on knowledge of biochemistry and disease. Remember Arthur Kohlberg, biochemistry, the father of biochemistry, from enzyme of gene replication, DNA biochemistry. At that time, in the DNA structures, biochemistry. This lady revolutionized drug development. Mega revolutions. Dr. Faber, this lady. I feel very blessed I have opportunity to give a talk in the same conference, in the same section as in Los Angeles in 1992 or 1991. After the presentations, we were invited to the high tea with Dr. Harry O'Swell. He was the president of Cancer Association. So we have high tea in the presidential suite in the hotel. And I sat next to her. We had a lot of chat. Wow, this woman, really knowledgeable, very humble. And suddenly she said, firstly, I want to have a drink, Coca-Cola. So I opened a bottle of Coca-Cola. And she said, I cannot eat the whole bottle, drink the whole bottle. I can share with you. So I share one Coca-Cola with a local logo. After 8 years, she passed away. After this conference, she passed away. So I always tell this story to my students, to my medical students and nursing students. So all China students, listen to this story. I think this is really a very, really meaningful story in my life. It's maybe like a revolution of the drug development. So what we are doing is also revolutionize the drug used for cancer treatment, to cure cancer. Okay. In China, one of the very good doctors, a good friend with me, and all his students also went into the committee. My student also, he joined the committee. Dr. Xie, she really admired B23. He loved B23, so he also came well with B23 in his patient, from his patient. This is really from his patients, hepatoma, liver cancers. So the liver cancer, he found out B23 is more overexpressed, more abundant. Okay, more abundant. Also, he did a lot of very good experiments, and he found out the polosis B23 overexpression is strongly associated with higher recurrence and lower overall survival. Published in 2013 hepatologists. Okay, so this is a very important clinical study. We came out in China. So I'm also very glad that I have the opportunity to visit Harvard and Stanford. At that time, my boy, my son, was a PhD student in Harvard Medical School Bioscience department. So I went to visit Harvard. And he introduced his supervisor, Dr. Lin, and he's from mainland China, and she did very good PhD work at the University of Michigan. After she graduated, she was recruited to Harvard to be a professor at that time. So she's really, really brilliant. She's a very good professor and humble. So when I visited her, she introduced me to a lot of professors at Harvard. Harvard and also Dana-Farber Institute. So I went there to talk to a law professor at that time to discuss with them about. So I visited Dana-Farber Institute. And also she introduced me one of the professor went to Stanford from Harvard. This is Dr. Wang Wenhong, is a very famous statistician. He's a medical department statistician, like physics. So he's not a biological scientist, but he trained half his office to build a DNA lab, and he hired postdoc to do DNA research. Using his half of office, big office, to just change a little bit section of his lab. So he loved to do some DNA statistics. Okay. So he introduced me to meet Professor Wang. Professor Wang. He felt a little bit embarrassed because my son applied for Stanford Statistics Department for PhD program, got rejected. So he went to Harvard. So he wrote there, oh, Harvard is better. he was rejected to go to Stanford. He was just only give offer to the master program, but he finally went to Harvard. So he met him, Professor Wang, and he invited me for a very nice dinner. After the dinner, he said, "Ben, you are from Harvard biochemistry department. I got a funding using statistics to calculate in the cell there are 20,000 genes. They calculate the gene co-expression index. What do you mean by co-expression index? So whenever I see you, I see this gene. So there's an index. Whenever I see this one, just see the co-expression index. You say, Ben, I'm not a biochemist. I just pass it to you. You use it for your biochemistry study. I just shocked him because our statistician, he feels that this is so will be very important, very useful. So I said, wow, just compare cancer cell and normal cell, see what happens. How the gene co-expression, the 20,000 gene interaction co-expression differ in cancer cell compared with the normal cell. This is what I got from the dinner talk to you. Wow, this is how we go on. Wow, when I saw this one, after my student compared the gene co-expression in the cancer as compared to the normal, you can see this is DNA. The co-expression index with this ribosome, V ribosomal protein, so closely, and linked to other ribosomal protein. The ribosomal biosynthesis in the nucleolus shuttle out to the nucleoplasm. Ribosomal protein. Before, nobody knows what ribosomal protein doing. But from this is extremely different level in cancer cell as compared to the normal cells. You see, cancer-specific linkages with ribosomal biosynthesis genes. And this ribosomal protein in the last 15 years, a lot of good paper, important paper, Nature and Science, talking about this ribosomal protein, how they correlate, associate with P53 in control of apoptosis, invasive metastasis, those cancer features. This is the first time we really elaborate more the origin of cancer, how glucose protein linked to fundamental regulation to cancer features. So at that time, I started my company because I felt all my 40 years of research can be implemented to clinical uses for patients. This is completely, I have never thought about my basic research, basic science research. One day can be used, clinical use for patients. You can see, you see a lot of interesting things in breast cancer. This is from patients' data, not from cell line. This is from patients. Each patient, their precious samples. We analysis the gene co-expression, B23 co-expression. You can see how B23 linked to these important oncogenes in control of the cell cycle, stress response, TGF-beta pathway, wave pathway in cancer, all those important cancer regulated pathways. B23 has a linkage in the cancers. Okay. Over connections of B23 to a cancer pathway. So I start my company basically 3 or 4 years ago, but we started the first funding 2 years ago. So I set up the motto for my company, my motto company. First, I use another Congress word. Good science always comes from simple and important person. For his presentation and lecture for many, many years, Arthur Comer must have this line. He told all the audience, good science always comes from simple and important person, from Arthur Comer. And my second motto is, Heracles, nucleolus is the origin of cancers. And my start company are using B23 gene co-expression. We find out this is lot of origins. The wave pathway, the apoptosis pathway, metastasis pathway. So many, many fundamentals, origins. So cancer has many origins. So this is why it's so difficult to cure cancer. There's many, many origins to make the cancers. So this is the motto of our company, BYQM. How I make this name? Quantitative medicine, because my professor Arthur Comer is about chemistry. Medicine is more or less qualitative at this time. Now we have co-expression index, the interaction index. We say this is quantitative medicine. This is the name coming out. And I try to using B23 as a company's name, but it's very difficult to say B23 company. And one of my good friends, a lawyer, a patent lawyer, he said, well, why don't you use your name, Benjamin Yuan? I said, well, yeah, Benjamin, B23, Benjamin B. And also, scientists will Professor Yuan doing B23. So we use it BY quantitative measure. And 中文名字为什么用以恩？以恩，我是一个基督徒，当时我有个孙女，我的 granddaughter， 我要改她的中文名字，我就很喜欢，我觉得我过去几十年的研究都是恩典啊，很难得。40年前我的老师叫我做 B23， 我就开始做 B23， 但是一直做下去这么多年 ，B23 的研究真的是很厉害。我看到都觉得哇，这很精彩，而且是可以帮助病人，所以我就用圣经里面所讲的以恩典为冠冕，所以什么都是从神的恩典来，所以就用以恩公司来开启我的公司的名字所以 OK，
好，我们做很多开始做一些很多 cancer 都做看很 special， 就看到很多精彩的东西。但是我们过去每年就 focus 在一个 cancer 跟女孩子有关系 ovarian cancer。那为什么我们选择 ovarian cancer？ 因为有几个原因啊。后来我们发觉最大的原因是 ovarian cancer 是非常 poor prognosis。ovarian cancer poor prognosis。The survival rate is very low. 如果我们能够帮助 if we can help the patients, ovarian cancer patients, this is high impact. Okay, so we focus on ovarian cancer for this last 1 or 2 years. So ovarian cancer, what are the key problems to be solved? Usually, when the ovarian cancer, we find out this is high-grade serous ovarian cancers, very poor prognosis, okay? They are very chemo-resistant, poor low response to chemotherapy, okay? About 40% in half a year become resistant to chemotherapy, low chemo. But standard protocol still only have this drug, cisplatin. Because still using this drug. Recurrent, still using the drugs. But in clinically, they divide into 2 groups. Half year, they become resistant. After a year, become resistant. So high resistant, low resistant, there are 2 groups. So we're using this GG co-expression patient to understand the biochemistry behind this low progress-free survival problem. Okay, so key problem to be solved. So interestingly, we found we identified some very interesting genes that co-associate beta-23. These genes are highly co-expressed with NPM1 compared with the low resistant patients. So, and this gene pathway also we find this a lot of drugs that can integrate this pathway. It's a lot exciting because that means this NGF pathway play very important role for anti-apoptosis, growth and differentiations in cancer. And we find out the origin of this ovarian cancer. For this cancer being poor prognosis, resistant, early resistant, and also survival rate is death. So if we can intervene this pathway when the patient is diagnosed with ovarian cancer at that time, if we know this pathway already, we have more choices of the drug. The drug revolution, the drug development, based on biochemistry, cancer biochemistry. Now you can think about how that lady revolution, the thinking of drug treatment therapy for cancer. Now we have a method, we have a biochemistry for integrating this important NGF pathway. And to remind you, these are identified from our GG co-expression platform from the cancer gene data. Okay. See, rather, NGF pathway, we find 19 pathways. I just show you one few here. See, and they all have a target. And this is very interesting. When we showed it to the one professor in Anderson recently, so he was shocked because people still argue about how estrogen played a role in the ovarian cancers. Now he saw there's a drug can integrate the estrogen pathway, the receptor, can reverse the growth, cell cycle progressions, invasion, the chemo resistance. This is for ovarian cancer. This is one of them. Now, all this data are from about 50 patients at that time. Why I call this, my title of my talk today is called Mission Impossible. Last year, being president and chief scientist of the company, I made important decision, the vision, how to move forward. 50 patients. Can we download all the data from the public domain as much as possible? See how many patients' data can be downloaded and analysis. This is a mission impossible because a lot of data from different hospitals, different laboratories, using different platforms, microwave, RNA sequencing, that kind of thing. How can we normalize all these data sets? I think we need to try. Go to this mission. So my staff working very hard, trying to download so many thousands of data, but finally we can only use 450 patient data. But this still allow normalize data processing to allow work to make the analysis. Now I'm good out. So I won't tell you how difficult the way it is. 开始没有。替我鼓掌。好，我告诉你，我们从这450 data set from patient data, we analysis 经济 B23 经济 co-expression. Wow, those important fact pathway that we found out in the resistant patients, cancer patients. Wow, this is the domain that we find is very significant different from the low resistance. You can see telomere maintenance, mitochondria making organization, generation precursor, metabolic energy, mitochondrial respiratory chain complex assembly, translation, RNA binding. All these are fundamental biochemistry. I was shocked. I'm shocked because it seems this is the origin of cancer features. We find out the mitochondria. Remember what mitochondria do? ATP energy production. Remember those pathway? Site 1, Site 2, Site 3, ATP, ATPase. Wow, those enzymes, those proteins being paired with an important role. They play very important role in cancer origins, pathways. On our platform, we got this result. So now we are working hard to make a story out to understand how this biochemistry working on the cancer features. Okay, let me show you some example. The telomere. Why I'm so excited about the telomere? Because at Taiwan, when I was at Stanford, telomere activity were discovered in complex laboratory. At Stanford, some other professor doing enzymology in telomere. So we talk about telomere at that time so much. So I'm so excited my NPM 1 is associated with the telomere maturation. You see the cancer, somatic cell undergo a finite number of division before entering senescence. See, going to senescence, cell divisions. Thereby preventing the generation accumulation of pathological genetic abnormalities. Other diseases, pathology also involved. Cancer cells capable of circumventing these defenses exhibit enhanced proliferative ability, heightened capacity to evade growth suppression in cell death signal. malignant transformation, cancer transformation, telomerase activation occurs in the context of telomere crisis, which facilitate the stable propagation of cancer-promoting genomic evaluation while limiting the excessive accumulation and senescence-induced mutation and structural aberrations. You see, something happened in cancer in these regulations. Genomic instability, sustaining prolific loading, evading growth suppressor, resisting cell death, inducing angiogenesis, immunomodulation, activating invasion metastasis. All these cancer transformation features are originated from these telomere maintenance with NPM gene interactions. So we discover this important. You can see complex of telomere enzyme, NHP2 interact B23, one of the protein co-expressor with NPM1, maintain this important regulation for cancer growth and for normal growth. So you want to explain. Okay. And also from literature, found that the gene that we also identify is a key factor in the early stage of malignant transformation by regulating telomere maintenance. Okay. So upregulation of this gene, you see, P53, very pathway, HER2 is very famous gene composite, significance of telomere activation and regulation in cancer. So this is what we find by our study. Okay, let me using the last few slides to show you our platform. Our gene co-expression platform, using the patient data processing and normalization. Then we go for our gene co-expression test, KS test, and also we did the differential expression analysis. We obtained the list of resistance specific gene, I showed you before. Then using informatic biological pattern enrichment, where a microscopic and interconnected microscopic view of mechanism of disease. You see there's a lot of study in vitro study, microscopic view of oncogenic pattern. Now we can see the whole thing together because of the patient all 20,000 gene co-expressions. Then we can see all the macroscopic view, how the immune response modulation linked to metastasis pathway or oncogenic apoptosis pathway. So we can see in one big microscopic and macroscopic view. And these two words are very interesting to me because when I was at Stanford, a lot of postdocs we talk about this, this is macroscopic view. Like in physics also, macroscopic material, microscopic, we are talking about environment of cancer. So this is what we do. So we're using AI machine learning to try to give some mathematical index to see the gene. So how this gene are more significant or more important than other gene sectors. So this is what we're trying to do. Okay. So when a patient tumor sample, once we diagnose the cancer, so after surgery, we use her sample. Before any treatment, we do the RNA sequencing, gene co-expression data. As I say, we provide the mechanism of disease, pathology, and biochemistry, and related to cancer features. For the ovarian cancer, we try to make the index for them. This patient is the high risk for chemo-resistant, for intermediate risk or low risk. Then we can suggest, we can recommend, the doctor can recommend for high-risk patients, no chemotherapy could be recommended. Since there's no use at all for chemotherapy, chemotherapy is very toxic. So maybe this patient recommend not to use chemotherapy. Maybe recommend way to use those drug target that we find from those biochemistry panel. So we can index for these patients. Maybe for low risk or intermediate risk, they can combination with chemotherapy and personalized targeted therapy. Okay, so this can be help medical doctor to make decisions for disease management. This is very important concept nowadays. Cancer is very difficult to cure because too many things happening. Origins. Now when we understand the origins more, the biochemistry more, then we could manage it better. So the data we obtain for analysis way away from the tumor sample before any tumor is so precious. Because along the tumor, wow, we know this patient is resistant or tuberculosis after half a year. We still have the data, the early stage data. We look at the data again and again, try to understand, to explain why this cancer is so invasive metastasis, so we can provide information along the treatment, the management. Hopefully, we can get better management for this disease, so you can suffer less from the chemotherapy, and maybe you can get a lot help. One of the important advice, I'm not a medical doctor, but I can provide the patient, if you have friends have cancer, the respiration mitochondrial mechanism is so important. That means breathing, exercise, energy, oxygen, oxidative phosphorylation pathway is critical for cancer process, because producing ATP energy or energy is crucial for patient recovery. That easy, you can tell your friend, go out, breathe air, healthy exercise is so important for prognosis. So this is a lot of very important information for the prognosis. Okay, we can see what we can do. Our gene co-expression model is a novel, innovative, industrial applicable this way. We apply for patent. This is the comment they gave us. This is for the top comment that we received. The gene test predict patient respond to standard chemotherapy, permit us precise risk assessment, and improve personalized treatment. For resistant high-risk patient, chemotherapy is not recommended, while personalized target therapy strategies could be made. Resistant intermediate low-risk patient, combination chemotherapy and personalized target therapy could be recommended. So this is called the disease management. Personalized understanding of the genetic transcriptome profile of the patient cancer, and also include the expression level, the key gene linked to chemo-resistant, the refiner, that is really informative and useful for the disease management. A potential collaboration in the field of biotech and also pharmaceutical company, and also traditional Chinese medicine, because a non-traditional Chinese medicine have also many important pathway effects. Oncogenic or apoptosis, Berkeley-induced apoptosis, a lot of pathway already know. So this can be used for prevention or cure of cancer, prognosis cancer. So I think this is the last line. I think this, I stop here. Okay, thank you very much for your attention.